In this video, we'll take a look at how to find zeros of polynomial functions. Or another way to think about it is, if you take your polynomial and set it equal to 0, how do you solve it? We've already solved linear functions and quadratic functions by using the quadratic formula, but what do you do when your functions are cubic, quartic, quintic, or higher degree polynomials? So first thing we're going to look at are theorems that are going to help us be able to do this. So one theorem that we're going to take a look at is something called the remainder theorem. It says if a polynomial f of x is divided by x minus k, then the remainder is the value f of k. So what does that mean? Here's an example. Using the remainder theorem to evaluate a polynomial, use the remainder theorem to evaluate this polynomial at x equals 2. All right, so basically what we're going to do is use synthetic division to divide f of x by x minus 2. If x equals 2 is the solution, then x minus 2 equals 0 would be a factor. So we take synthetic division, we have 6 x to the fourth minus 1 x to the third minus 15 x squared plus 2x minus 7. So we start with x to the fourth. Every value is there, so we don't need any zeros. And we're going to divide by x minus 2, so that means positive 2 goes on the outside. So follow steps for synthetic division. Carry down the 6. 6 times 2 is 12. Negative 1 plus 12 is 11. 11 times 2 is 22. Negative 15 plus 22 is 7. 7 times 2 is 14. 14 plus 2 is 16. 16 times 2 is 32. 32 minus 7 is 25. So what the remainder theorem means is if you divide this function by x minus 2, the remainder is 25. That means when you find f of 2, when you substitute a 2 into the function itself, 6 times 2 to the fourth minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7, f of 2 is going to equal 25. So when you evaluate a function at x equals 2, you get the remainder, the same value, 25, if you divide the function by x minus 2. So that's called the remainder theorem. So what if the remainder is 0? So according to the factor theorem, k is a 0 of f of x if and only if x minus k is a factor. So that means if you were to put a f of 2 in here and it equaled 0, oh, that means it would be a 0. That means it would cross the x-axis at 2. In this case, you didn't get 0, so it doesn't cross the x-axis at 2. F of 2 gives you the y-coordinate. Okay, so the factor theorem, factor the following expression completely given that one of the roots is negative 6. So we don't have a way to factor an expression like this unless we use grouping. So we can't use grouping here, but we do know that one of the roots, so one of the solutions, is x equals negative 6. That means when you take x to the other side, that means that x plus 6 is a factor. That means it goes into this evenly. So how do you factor the expression completely? Well, divide x plus 6, divide this expression by x plus 6, and see what you have left. So using synthetic division, let's see, I should use y because that's the appropriate variable here. So we're going to use synthetic division. We're going to take 1y to the third, 14, y squared, 63y, 90, and we're going to divide it by, if the root is negative 6, the factor is y plus 6, and we put a negative 6 on the outside. Synthetic division, carry down the 1. 1 times negative 6 is negative 6. 14 minus 6 is 8. Negative 6 times 8 is negative 48. 63 minus 48 is 15. 15 times negative 6 is negative 90. And we get a 0. The remainder is 0. So what that means is y plus 6 is a factor. And when we divided this out, we're left with y squared plus 8y plus 15. Now I can take a look at the quadratic and factor it using techniques for quadratics. So y goes in the first spot. Two numbers whose product is 15 at the same time the sum is 8 is plus 3 and plus 5. So we can fully factor this expression into y plus 6 times y plus 3 times y plus 5. So we can factor a polynomial if we know one of the factors. We can divide it out and then factor it the rest of the way using techniques that we learned in the quadratic chapter. All right, so that's the factor theorem. The next theorem we need is something called the rational zero theorem. A rational number, if you remember, is a number where your value will cross the x-axis. The rational zero theorem states that if the polynomial has integer coefficients, then every rational zero has the form p over q, where p is a factor of the constant term, a sub 0, and q is a factor of the leading coefficient, a sub n. So rational zeros, rational numbers are fractions. So we're trying to find, this tells you that given this function, p of x equals 2x cubed plus x squared plus 2x plus 1, this is how you narrow down possible factors. In the previous example, they told us that one of the roots is negative 6. If you don't have that to start with, this tells you, the rational zero theorem tells you, it gives you a place to start. Okay? So given the function, list all the potential rational zeros. All right, so what does this say again? Every rational zero has the form p over q, where p is a factor of the constant term. So p in this case is the constant term, which is 1. The only factors of 1 are 1 and itself, either 1 times 1 or negative 1 times negative 1. Q is a factor of the leading coefficient a sub n. The leading coefficient is 2. The factors of 2 are 1, negative 1, 2, negative 2. Then the rational zero has the form p over q. If you take a look at the factors p, factors of q, can you divide them and come up with more factors? Well, we could have 1 over 1, 1/2, and negative 1/2. So in this function, the potential rational zeros are 1, negative 1, 2, negative 2. Those are actually the whole numbers, 1/2, and negative 1/2. So any of those are potential zeros. All right, so one more idea, a general note. The fundamental theorem of algebra says that if f of x is a polynomial of degree n greater than 0, then the f of x has at least one complex zero. What does this mean? So basically what we use with that theorem is if f of x is a polynomial of degree n, then f of x has n linear factors. So that means if your polynomial has degree 3, then it should factor into some constant times x c1, c2. So if your original polynomial has degree 3, then it can be factored into 1, 2, 3 factors. Okay? And some of those might be complex numbers. So all of these theorems together are going to let us solve a polynomial or find zeros of a polynomial function. So given a polynomial function, here's how you solve it or find all the zeros. Number one, you use the rational zero theorem to list all the possible rational zeros of the function. Two, use synthetic division to evaluate a given possible zero and see if the remainder is zero. If it's not zero, discard. Repeat step two using the quotient found with synthetic division and then continue. So what does that mean? We want to find the zeros of this polynomial. I've got it graphed below. So the possible rational zeros, if you take a look at the polynomial, you look at the factors of 4. Factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4. That means, and then look at the factors of 2, plus or minus 1, plus or minus 2. Then see if you can create any fractions. This is P, these are Q. See if you can create any other values with P divided by Q. We have 1 over 1/2 plus or minus 1/2. So these are all candidates. Instead of trying each of them inside the function to see what works, graph the function and see where it crosses the x-axis. This happens to cross at all three. -4, it crosses at 1/2, and it crosses at 1. So those are the three zeros, and we got it graphically. We should be checking using the graph, so I'll show you how to do this by hand. Use one of your zeros. Let's say that you found out that x equals -4. So we're going to use -4 as one of the zeros. Okay? If x equals -4 is a zero, then x plus 4 is the factor. So we divide this equation, polynomial, by x plus 4. That means -4 goes on the outside, and we get 2, 5, -11, 4. Do your synthetic division. 2 times -4, -8. 5 minus 8 is -3 times -4 is positive 12. We end up with 1 times -4 is -4. We end up with a remainder of 0. So once we divide by x plus 4, we're left with 2x squared minus 3x plus 1. Then factor that expression. We get 2x, x, 1 times 1, and they both have to be negative in order to get a -3x. Then once you have all three of these, x plus 4 is still here. Set each equal to 0, and those will give you the zeros. So x equals 1/2, x equals 1, and x equals -4. So that's how you use synthetic division. It just so happened in this one that all three crossed the x-axis at integer or fraction rational points. So what if, next example, we want to find all the zeros of 4x to the third minus 28x squared plus 47x minus 35. Well, this time I graphed, and notice it only crossed the x-axis once, and it looks like it crossed right here at 5. So we want to make sure that we have all of the entire solution. It's a cubic, so that tells me that one solution is a real number and the other two are complex numbers. So it looks like it crosses at 5, so check and make sure that that works. If it crosses at 5, x equals 5 is a 0. That means x minus 5 is a factor. So divide synthetic division. I have 4x to the third minus 28x squared plus 47x minus 35. And we're going to divide that by x minus 5. So that means positive 5 goes on the outside. I carry down the 4. 4 times 5 is 20. -8 times 5 is -40. We end up with 7 times 5 is positive 35. And that should happen. We get a remainder of 0. So that means that x equals 5 is 0. And when we divide it out, we end up with 4x squared minus 8x plus 7. Now I want to take that and set it equal to 0. I know it's not going to factor because looking at the graph, it's going to be complex numbers. So we're going to use quadratic formula. A is 4, B is -8, C is equal to 7. So x equals negative b, so that's -8, plus or minus the square root of b squared, -8 squared, minus 4 times a, which is 4, times c, which is 7, all over 2 times a, which is 4. So we should end up with a negative inside the square root. So I get x is equal to 8 plus or minus the square root. I'm just going to put that in the calculator. That's going to be 64 minus 112, which ends up being a negative 48 inside the square root over 8. Now I simplify. 48 is divisible by 16. The square root of negative 48 is the square root of negative 16 times 3. So when I take the negative 16 out, it becomes 4i square root of 3. So we're on the last step, which is simplifying. Let me scoot this down and get some room. So my last step is I get x is equal to 8 plus or minus 4i times the square root of 3 over 8. Notice each of the terms 8, 4, and 8 are divisible by 4. Factor of 4 out of the numerator and then cancel. So I get 2 plus or minus I square root of 3. Again, we factor a 4 out of the numerator and cancel over 2. So now, entering the exact values, find my zeros and separate them by commas. The zeros are at 5 is one of them. 2 plus I square root of 3 over 2. And 2 minus I square root of 3 over 2. So those are the 3 zeros. And then the graph let us know what our first rational zero was. And then we had to use quadratic formula, synthetic division, then quadratic formula to find the other 2. All right, last couple of examples. Example 7, use linear factorization theorem to find a polynomial with the given zeros. If we want a 4th degree polynomial, then we need 4 factors. And it says it has zeros of -3. So that means that x equals -3 is a solution, x equals 2, x equals I, and complex numbers occur in complex pairs. So if I is a solution, automatically -I is a solution. They occur as complex conjugates. So what I'm trying to get is a 4th degree polynomial, f of x, equals a times x. I've got my 4 factors. I've got my 4 solutions. So now I know that my polynomial is going to be of the form f of x is equal to a times x plus 3 is the factor, times x minus 2 is the factor, times x minus I, times x plus I. I'm going to leave the a where it is and then multiply, find a 4th degree polynomial. So if I multiply that out, I end up with a times, let's see, x plus 3 times x minus 2, I get x squared, plus 3x minus 2x is plus x, 3 times -2 is minus 6, x plus I times x minus I get x squared. The middle terms will cancel. I get negative I squared. I squared is -1, so that ends up being plus 1. You can multiply this out if they need it multiplied all the way through. Take x squared times x squared, I get x to the 4th. I still have that a in the front. X times x squared is x to the 4th. X times x squared is plus x cubed. Let's see, -6 times x squared is minus 6x squared. then multiply, let's see, x squared times x squared, x to the fourth, then multiply each of our terms by 1. X squared times 1 is plus x squared. X times 1 is plus x. 6 times 1 is negative 6. Add like terms. I end up with x to the fourth plus x cubed. Negative 6 plus 1 is minus 5x squared plus x minus 6. Now, to find out what that a is, this is what the given point is for. It tells us that f of negative 2 is 100, so substitute 100 in for f of x and substitute negative 2 in for x. So I get negative 2 to the fourth plus negative 2 cubed minus 5 times negative 2 squared plus negative 2 minus 6. Add together, negative 2 to the fourth is a positive 16. Negative 2 cubed is minus 8. Let's see, negative 2 squared is positive 4 times negative 5 is negative 20. Negative 2 plus negative 6 is negative 8. Add these together. I get negative 20. So 100 equals negative 20 times a. Divide both sides by negative 20. And a is equal to 100 divided by negative 20 is negative 5. So if I want to put it in factored form, my polynomial would be negative 5 times x plus 3, x minus 2, and I could also have that x squared plus 1, or if you want it multiplied out, f of x would be your result when you take negative 5 and multiply it through your polynomial. Negative 5x to the fourth minus 5x cubed plus 30x squared minus 5x squared. Let me get that. I already added that up over here. I'll use this one. So negative 5x to the fourth minus 5x cubed. Negative times a negative is plus 25x squared minus 5x plus 30. So there's the polynomial in long form multiplied out and the polynomial in factored form without complex numbers. All right, last example. We'll set it up, but won't multiply it out, but you'll get the same idea. So last example, the polynomial of degree 4 has a root of multiplicity 2 at x equals 2. So remember, a multiplicity 2 means at x equals 2, x minus 2 is the factor, but it occurs twice. It has multiplicity of 2. And roots of multiplicity 1 at x equals 0, that means your factor is just x, and x equals negative 1. So that factor would be x plus 1. So if you want to find a formula for your polynomial, it's a times these multiplied together. And you might be okay with leaving them in factored form. X times x plus 1 times x minus 2 squared. Okay? To find a, substitute your coordinate 1, 6 in for the polynomial p of x is 6 is equal to a times substitute 1 for x. And you end up with negative 6 equals a times 1 times 2. Let's see, that would be negative 1 squared is a positive 1. 6 is equal to 2a, so a would equal 3. So in factored form, your polynomial is 3 times x plus 1 times x minus 2 squared. And that's the factored form, and that might be fine. Or if homework wants you to multiply it out, you would multiply this out. But I think factored form will probably be okay.